Bismillahirrahmanirrahim. So today we will be having our 15th lecture and we will be discussing about comparators and multiplexers, right? So these are the bullets which we will be going through one by one. First we will be discussing comparators. We will start from 1-bit comparator, then we will move towards the multi-bit comparators or more than 1-bit comparators, right? And then we will study about multiplexers, why we need multiplexers and how we normally use those multiplexers according to our requirement, right? So let's start. So let's talk about comparators, right? So in computer programming languages, you normally come across the comparison of two variables. You normally have to compare two variables, so there can be three different possibilities, right? One, the two variables, they are equal, right? And the second, one variable is greater than the other, and the third possibility is one variable is less than the other, right? So we will do the same but in our digital logic design, and we will start from the first bit comparator, 1-bit comparator, right? So normally comparators interpret the input, right, as a signed number, right? And another point which I would like to mention, that with the help of comparator, you can find the relationship, right, between these the words that are being compared with each other, right? So we can have circuits that are called magnitude comparators, right? So the basic building block that is being used while designing the comparator circuit is XOR, NOR, although we will start designing those comparators from the basic logic, that is AND or NOT, but ultimately we will move towards XOR, XNOR, right? So we will obviously design the combinational circuits, right, that will be able to compare, right, or find the magnitude. So whenever we talk about comparators, right, so we normally come across very common operation that is being performed in computer programming, right? We have to compare two variables, right? And there can be three different possibilities. The variables can be equal, one variable can be greater than the other variable, right? And the third possibility is that the one variable is less than the other, right? So here we will be designing a circuit that is going to compare two binary words, right? And we will find out either the two binary numbers, they are equal, they are if one is greater than the other, and the third possibility, then the one is less than the other, right? And some of the comparators, right, they are based on the signed and unsigned numbers, right? And as a matter of fact, we can have the arithmetic relationship between those two different binary numbers that are being compared, right? So we, on the basis of that, we can say that the circuit that that is being used is called the magnitude comparator, right? Although we will start from the single bit comparator, then we move on to the comparator that can compare more than one bit, right? And we will be using the basic Boolean logic, that is AND or NOT, right? And then we will design comparators by using XOR and XNOR gates, right? So ultimately we will be designing the combinational circuit, right? Okay, so let's talk about the functionality design of comparators, right? And we will start from 1-bit comparator, right? So we have two variables, right, each representing a bit, right? So A can have two values, right, 0 and 1, because we are talking about binary, and B can also have 0 and 1, right? So this is a sort of K-map, right, this one, and you can see that we have B in the horizontal direction and A in the vertical direction, right? So here if we have to represent the three different possibilities that are A is equal to B, A is less than B, A is greater than B, and here again A is equal to B, right? So if you look at the values that A and B can have, so here A is having 0 and B also has 0, right? So A is equal to B because they both have the same value. So here A has 1, right, and B has 0, so A is greater than B, right, because A is having a value of 1 and B has 0, right? So here if you look, right, so A is 0, right, because A is 0 and B is 1, right? So A is less than B. Again here we have both A and B has 1 each, right? So A is equal to B, A having 1 and B also has 1, right? So if you talk about the min terms, so for this case, when A is less than B, we are having, right, so A bar B, right? So let me write down, or you can straight away look here. So this is the A bar B, right? And here we have for A greater than B, so we will be having A and B bar, because this is 0, so we will normally take the complement whenever we have a 0, right? And we will be having A B bar, right? For the equal scenario, we have two values, right, A bar B bar, and then here we have A B, right? So this is A bar B bar plus A B. So if you have to design a circuit then that can represent this functionality, so this is the circuit, logic circuit, right? So you can see we have two inputs, right, A and B, and we have three outputs, right? This is for representing A greater than B, right, and this is A is equal to B, and this is A less than B, right? And that will work out, right? So if we will operate this circuit by taking one of the values, right? So let me write down the different values. So this is for A greater than B, so we will have A B bar, right? And this is for, so this is A B, right? And this is A bar B bar, right? So we'll be having A bar B bar plus A B, right? And this is, let me write down straight away, right, for less than A bar B, right? So actually what we will get A B bar, right, plus A bar B bar, right, plus A B, right? We will be having NOR operation, right? So this is for NOR. So when we will solve this, we will get A bar B, right? You can solve this. So let's talk about when we have both A and B equal, right? So we will focus here, right? So what we will be getting, A B, right, is equal to 1, right, and A bar B bar, right? So this is 1. So here we have 0, right, and here we also have 0. So this is the case when we are having A and B equal, right? So let's talk about 1, 0, right? So what we will be having, right? See, this is when we have equal, right? And here A, right, and B bar. So we will be having 1 here, right? And what about this, right? We will be having a 0 here, right? And we will be having a 0 here, right? So it means we have verified our circuit. So it is working for 1 bit, right? And now we can have this logic circuit, right? So you can see the only difference is we have added a control over here, that is the enable, right? So we can control. So you can see that if we are able to make this circuit working whenever we turn on the enable, when we will be having enable is equal to 1. So let's check this, right? So here if we have two values, right, like let's say 1, 1, right? So you know that for A is equal to B, we have A bar, B bar, right? Right? So this is and you can see that whenever enable is 1, right? So this is 1, so we will get 1, right? For A greater than B, we will be having, let me check this, right, A, B bar, right? So we will be having a 0 here, 1 here, and we will be having a 0 here, right? And whenever we will be having enable 0, so we will be getting, right, 0. So enable is a sort of control signal, right? And then we can also design a circuit, right, that can compare more than 1 bit. So here we have you can see that the 1-bit comparators are connected or cascaded in such a way that we can have a circuit that can compare more than 1 bit. So here we have a 4-bit comparator, right? So let's talk about 2-bit comparator, right? So let's the problem is that we have to design a circuit that can compare 2-bit number, right? So we have two numbers, A and B. Each number has 2 bits, right? And let's define some symbols. G for greater, right? If A is greater than B, then it is represented by G, right? And if both the numbers, binary numbers having 2 bit each, are equal, then it is represented by E. And if A is lesser than B, then we mention this with L, right? So as we know that each number, right, binary number has 2 bits, right? And how many different possibilities? For example, for A, right, we have A naught A1, right? So they can have 0 0 0 1 1 0 1 1, right? Similarly for B, we have B naught B1 0 0 0 1 1 0 and 1 1, right? So these are the different possible values those numbers can have, right? So this is the, you can say, block diagram, right? So we have 4 inputs, right? You can see we have 4 inputs, 1 2 3 4 and 3 output, right? G greater, E equal, L lesser, right? So this is the truth table, right? You can see that we have 16 different possible values if we have placed them in this order, right? A1 A naught, B1 B naught, right? So 0 0 0, right? 0 0 1, right? So 0 0 1 0. So you can see that we have 16 different combinations, right? So here we have 0 0 0 1 1 0 1 1, so right, A1 and A not all are 0, right? So here we have 0 1, right, 0 0 0 1 1 0, right, and then 1 1, right? So here we have 1 0 0 0 0 1 1 0, right? So we are fixing A1 and A0, and then we are changing the values of B1 and B0, right? So we have 16 different combinations, right? So because as I have mentioned, so we have 3 different output, right? So here let's draw the K-maps, right? Because we are moving towards the circuit design for a 2-bit comparator, right? So the problem is that we have 2 numbers and each number has 2 bits, right? So we have to compare them. So we first have drawn the truth table, right? And we have shown all the possible values, right? And then we have written the output, right? This is the input and this is the output, right? So here if you look, right, so both numbers are equal, right? Here you can see both A and B has 0 0 0 0, they are equal, right? So here we have 0 1, right, and 0 0, right? So it means A is lesser than B, right? And then we have 1 0, right, again lesser, A is lesser than B, right? So here lesser, right? So 0 1, right, 0 0, so here B is 0 0, right? And if you talk about A, right, 0 1, so it means A is greater than B, right? And then we have 0 1 0 1, they are equal, right, because both A and B have equal values. So here if you look here, right, 0 1 1 0, so it means B is greater than A, right? Or you can say in other words that A is lesser than B, right? So here 0 1 1 1, again lesser, right? So you can always have a look, right? So let's talk about the K-map. So we have to draw the K-map, right? So let me write down the values. So we are focusing on G here, right? So we will start from M0, right? M1, M2, M3, right? M4, M5, M6, M7, right? M8, M9, right? M10 and M11, right? Here M12, 13, 14 and M15, right? So I will be mapping this over here, right? So 0, 1, 2, 3, right? And then we will be having 4, right? 5, 6, 7, right? So jump, right? 8, 9, 10, 11, right? So here I have to write 12, 13 and 14 and 15, right? Right? So you can see that here we have 1, right? M4, so here is the 1, right? Then we have M8, right? Where is 8? 8, 1, right? And 9 is also 1, right? And then we have 12, where is 12? So here 12, right? 13 is also 1, right? And then 14, 1, right? So now we will be looking for the pairs. So first we will start from the quad, right? Because this is a 4 by 4, right? So you can see that we have no quad, so then we will look for the squares, right? So here we have a square. So as a result of this square, right, what we will be having, we will be having A1 B1 bar, right? And then we will look for pairs, right? So if you twist and bend, right, so here we have this one and this one, right? So as a result of this pair, we will be getting A1 A naught B naught bar, right? And then we have this pair, right? So this pair will generate this term, right? A naught B1 bar and B naught bar, right? So actually what we have, if you talk here, right, so we are having A1, right, A naught, right, B1 B naught, right? So here we have 0 0 0 1 1 0 1 1, right? So similarly we have a 0 0 0 1 1 0 1 1, right? Sorry, I have to change this, right, because we normally take a jump, right? 1 0 1 1, right? So here again 1 1 1 0, right? So if you look here, right, so here we have right, this, right? So we will be having the Boolean expression for G, right? So you can have A1 A naught B naught bar A naught B1 bar B naught bar plus A1 B1 bar, right? So let's move to the equal, right? So you can see that we have the truth table, right? So this is the equal, right? So I will be, so here we have 1 at 0, so right, you can see 1, right? Then 1 2 2 3, right? And then we have another one here, right? So this is 1, right? And then this is the 1, right? Right? So we have a 1 here, right? And then we have the final one here, right? So you can see that this is a sort of diagonal, right? We have all ones in the diagonal, right? So there cannot be any pair, right, or groupings. So we will be having a very long term for each one, right? You can see that here we have A1 bar, A naught bar, right? B1 bar, B naught bar, right, for this one, right? And then for this one we have this term, and so on and so forth. This is for the equal, right? And then we will be talking about for lesser L, right? So here you can see that we have a 1 at first position, right? So 0 1, and then third and fourth, right? And then we have 0 1 2 third, right? So here we have 1 2 and third, right? And then we can have 1 here, right, here. So let me again write down the min terms, right? So we have M0, M1, M2, M3, right, M4, M5, M6, M7, M8, M9, M10, M11, 12, right, 13, 14, and 15, right? So I will be writing 1, 2, and 3, right? This is 4, 5, 6, 7, right? And we will take a jump 8, 9, 10, 11, right? 12, 13, 14, and 15, right? So now we will be placing the ones, right? So you can see that we have a 1 here, right? M1, so this is 1, then M2, this is 2, right? And M3, right? And then we have 1 at 6, right? M6, right? So here we have a 6, 7 is also 1, right? And then we will be having M11, so here 1, right? So now we have all ones that are mapped to the K-map, right? So now we will be looking for the groupings. So here we have a square, right? So as a result of this square, we will be having A1 bar B1, right? And then we have a pair here, 1 after bending or twisting, right? So we have A0 bar B1 B0, right? And then for this pair we will be having A1 bar A0 bar B0, right? So we now have the, so these are the Boolean expressions for G, E and L, right? So and this is the circuitry for G, right? So you can see that we have managed the complement externally, so B0, right? So this is the B0 bar, right? And then here we have two complements, B1 is complemented and B0 is complemented. So we have handled them externally, right? So it means if I have to write down the output of each, right? So this will be A1, right? A0 and B0 bar, right? And here we will be having A0, right? B1 bar and A B0 bar, right? And here we will be having A1 B1 bar, right? So and they are added, right? So we have B0 bar plus, right, A0 B1 bar B0 bar, right, plus A1 B1 bar, right? So this is the circuit for greater, right? So let's have the, so for example, if we have the scenario, right, where A is greater than B, right? So let's talk about 1 1 and A1 A0, right? And then we have B1 B0 is 1 0, right? So if I put here, right, so A is, right, 1 1, and then this is not, right, this will be 1 plus 1, right, 1, right, and then this will be 0, right, and then this will be 1, right, because B0 is 0, and plus A1 1 B0 bar 1, right? So we will be getting a 1, right? And then this is the circuitry for less, right? And this is the circuitry for equality, right? So if we have two numbers, right? Right? So let's, if A1 A0 is equal to 1 1, right? And then B1 B0 is equal to 1 1. So if I put this here, you will get a 1, right? So this is the circuit for equal, right? And this is the circuit for lesser, right? So we can always have or you can see a closed form of this very long expression, right? So you can see that if I will take let me solve this, right? So what I have to do, right? So I have to take A1 bar and so A1 bar, right, and what else I can take common, right? A1 bar, right? And then B1 bar. I can take this common, right? So I will be having A0 bar, B0 bar, right? Then A1 and B1 is common, so A0, B0, right? So from here, what I can have, right? So I can have A1, B1 as common, right? So I will be having A0, B0 plus A0 bar, B0 bar, right? So this is the same, right? So now I can take this common, right? So I will be left with A0, B0 plus A0 bar, B0 bar, right? So this is common, and I will be having A1, B1, right? Plus A1 bar, B1 bar, right? So this is what, right? This is, I can take or write it as A0, right? Plus with a circle, so this is the conventional XOR, but I have to mention, right? And I can represent this as A1, right? B1 whole, right? So this is the closed form, or we have used here the XNOR, right? And then we can also have n-bit equal comparator, right? So you can see that we can have, if we look here, so A1, B1, A0, B1, if you have n bits, right? So you can have n-bit equal comparator, right? So, and this is the circuitry, right? So now we have introduced the XOR or XNOR while we are comparing bits, right? So if you look at the truth table of exclusive OR or exclusive NOR, so we will find something else, right? So here you can see that we are having the XOR, right? So if here you can see that if the two bits are equal, right? For example, this is A and this is B, right? Then we will have 0, and right, if we have two bits 1, 1, right, we also have the 0, right? So here is the case when the input bits are equal. So we will always get a 0 when the input bits are not equal, right? So then in that case 0, 1, 1, right? So we all know that in the truth table of exclusive OR, we say either A is high or B is high, right? We will get 1 but not the both, right? So here not the both, we will get 0. Either A is high, right? If you take this as A, right, and this as B, so either A is high, right, or B is high, right? So here we have we must have 1 0 case here, right? Either A is high or B is high, right? But not the both, right? So here you can see that when the input bits are equal, so we have to use that truth table in order to have the comparison. So here in the comparison, two bits are equal, we are getting 0, two bits are equal, we are getting 0, right? And they are not equal, right? So we are getting a 1, right? So this is the truth table, right? 0, 0, 1, 1, 1, 1. So these are the cases which we are interested, right? Okay, so let's talk about the design approaches, right? So we can use the truth table, right? as we did it before, right? But then it will be very difficult for us, right? If we have more number of bits, right? For example, if we have 5 bits, 6 bits or more, then it is not possible for us even to write down the truth table on a piece of paper, right? And then we can also have an algorithm, right? So that we have predefined number of steps in order to compare the two binary numbers, right? So let's talk about the approaches, right? So here we have two numbers, 4-bit each, right? Each number has 4 bits, right? So this is the circuitry, and you can see that we have A0, A1, A2, right? A3, B0, B1, B2, B3, right? So these are the outcomes of, so we are comparing actually each bit, right? So A0 is compared with B0, A1 is compared with B1, and A2 is compared with B2, right? So A3 is compared with B3, right? So if they are, right, we are having the output as C0, C1, C2, C3, right? And here we have the AND operation, D0, 1, right? So this is the 0 and 1, right? So this is 2 and 3, right? So D2, 3, and we have another AND, right? So we will be finding out A, either A is equal to B or not, right? So this is the way out how you can find that the two numbers are equal, right? So how we can find A is greater than B, right? So as we mentioned that here we have 8 bits, right? So how many number of different combinations if we draw the truth table, right? So as we have mentioned that we have 2 raised to power n, right? So where n is the number of bits for each binary number, right? So here 4, so we will be having 2 raised to power 8, right? 256. So this is not possible for us, right, to even draw the truth table on the screen or on a piece of paper, right? So what we need to devise an algorithm, right? We need to design or devise predefined number of steps so that we can, right, have this A, right? A, if we have to find out A is greater than B, right? So here let's have A is equal to 1, 0, 0, 1, right? And then B is equal to 0, 1, 1, 1, right? So is A is greater than B, right? So for me, yes, right? Why? Because if you talk about the most significant bit and the least significant bit. So here in the most significant bit we have a 1 and here we have a 0, right? So you can say that A3, right, if I mark them, right, as this is A0, this is A1, this is A2, and this is A3, right? And this is B0, B1, B2, and B3, right? So here you can see that we have A3 is greater than B3, right? So then we will be having this expression, right? So here A3 dot B3 complement, right? Because this is, because it can only take two values, so 0 or 1. So if we talk about the 0, we normally take the complement, right, when we normally compute the min terms. So here we have A3 dot B3 complement, this is 1, right? So this is the first term in our logic equation, right? So actually we are moving towards devising an algorithm in order to find A, if A is greater than B, right? So here if we have another scenario, right, 1 0 1 0 1 0 0 1, right? So let me write down the numbers A0, A1, A2, right? A1, A2 and A3, right? Similarly B0, B1, right? And B2 and B3, right? So here the question is either A is greater than B, right, or not, right? So here you can see this is we already know, right? And then we have C3 dot A2 dot B2 bar, right? And because A3 here, if you look here, A3 is equal to B3, right? And A2 and B2, they are also equal, but A1 is greater than B1, right? So it means we have C3 is equal to 1 because they are equal. C2 is also equal to 1 because C3 and C2 will be the resultant of those corresponding bits, right? And then we are having something here that is different. A1 dot B1 bar is equal to 1, right? So the next term in this equation, right, for A greater than B is C3 dot C2 dot A1 dot B1 bar, right? So so we can generalize, right? So now let's talk about the logic, right? So here you can see that if we have to compare the two numbers, so in case of their equality, if we want to know either the numbers are equal or not, right? So this is A and this is B, right? So here you can see that we have 4 bit, right, for A and 4 bits for B, right? So what we will be doing, we will be comparing the corresponding bits. So this will be compared with this will be compared with this, right, and so on and so forth. So you can see we will compare A3 is equal to B3, yes or no, right? So we will compare the corresponding bits, right? So here we have 0, right? Then this is the general expression, right, for equality, right? So we will be using the conventional XNOR, right? So this is A, let's A1 B1, right? So we also know that 0 0 0 1 1 0 1 1, right? So in case of XOR we have 0 1 1 0, right? In case of XNOR we have 1, right, 0 0 1, right? So you can see that when 2 bits are equal, we are having 1, right? And when the 2 bits, they are not equal, we are having 0, right? So here, this is the generalization of the XOR expression, right? So we are having A1 B1, right, plus A1 bar B1 bar, right? And then this is the most difficult is to test either A is greater than B or A is less than B. So now if we move back, so we have derived the expression for this, right? So you can see that these are the A3 B3 bar, right? Then this is X3, right? A2 B2 bar plus X3 X2, right? And X3, and then we are having X3 X2 A1 B1 bar, and so on and so forth, because we have 4 bits. So this is the expression for, or equation for 4 bits, right? So for A less than B, you can see that we have complemented, right? So this is A3 complement, right? So if you go back, right, so in case if we have, right, the scenario, then if A is equal to 0 1 1 1, right, and B is equal to 1 0 0 1, right? So you can see that now we will be taking the complement of A, because A is 0, right? So same is happening over here. So rather than taking the complement of B3, we have taken the complement of A3, right? So similarly A2 complement B2, and so on and so forth, right? So normally we start the comparison from the higher bit, from the most significant bit, right? So this is the generalized expression, right? So, and this is the IC which we can use, and you can see that we have the data sheet for this IC, and we have different data inputs, right? So we have, if you have to compare two numbers, this is for A's and this is for B's, right? And we will be having something here regarding A greater than B, and then this is for A is equal to B, and this is for A less than B, right? So this is the IC which we can have whenever we have to compare. And this is the application, right? So you can see that we have a temperature sensor over here, right? And this is the same comparator IC, right? 74HC85S, right? So, and as you know that we all know that the temperature is an analog quantity, so we have to use an A to D converter, right? So the temperature is converted to the digital form, right? After digitization, we will be applying at the input, right? So A0 to A7, right? So it means 8-bit number, right? So, and then we can have the keypad, because this is a thermostat controller, so you have to control the temperature, right? So here you can input the temperature by yourself, and this is the temperature from the environment, right? Taken from the sensor, right? So, and then the keypad values that are encoded, right? And we represented those values with B, so again 8 bits, right? So here you can see that we have the comparator, right? And here this is the flip-flop which we have not studied yet, right? So this is the actually the application of magnitude comparator. So this is the furnace controller, right? So you can control the temperature of this furnace, right? And let's move to the other topic, multiplexers, right? So normally when we talk about the data transmission, right? So what normally we have a very high-speed link between big cities, right? And within the city or between small cities, we have the links that don't have huge capacity. So what normally we do we multiplex the lines with smaller capacity over to or onto the link with a high capacity or high speed link, right? So for that functionality, right, we use multiplexer, right? So you can see that multiplexer is a device that allows several low speed signals to be sent over one high speed link, right? So actually the functionality is that we are selecting the lines, right, one of the lines, and that line is being sending its data, right, to the high speed link, right? And the demultiplexer performs the inverse or functionality or the opposite functionality as the multiplexer does, right? So there is one point which I must mention, that in order to have the true data, right, the multiplexer and demultiplexer should be must be synchronized, right? Then we can have different type of multiplexers, time division multiplexing, right, in which we slot a time, we assign a time slot for each line, right? And then we can also have a frequency division multiplexing, right? Okay, so this is the animated diagram of a multiplexer. You can see that we have the input lines, right, and the selector, right, or in other words the multiplexer is multiplexing all those different input lines onto a single line, right? So it is assigning a time slot, right? This is a TDM, right, time division multiplexing, and you can see that a time slot for each input, right? So, and this is the control switch, right? So when we have S1, S2, 0, 0, you can see that we connect ECE, right? Whenever we have S1, S2, right, 1, 1, so we connect CT, right? So this is the control signal, right? So we can have n control inputs, right, and then 2 raised to power n data inputs, right, and 1 output. So you can see we have 1 output, right? So here we have 4 different inputs, right, and to control the 4 inputs we need 2 raised to power 2, right, 2 raised to power 2 control lines, right, control inputs. So you can see that we have 1, 2, 3, 4, so 2 raised to power 2, 4, so we need 2 control lines, right? Okay, so this is the block diagram of the multiplexer. So you can see that we have 2 inputs, right, and 1 output, and this is the control input, right, as I have mentioned. So 2 into 1 multiplexer, right? So these are the data inputs, I0, I1. This is the control signal, right? So if I want to have the Boolean expression for this Z, which is the output, so you can see we have A0, right, I0. So when A is 0, I0 will be selected, right? So when A will be 1, I1 will be selected, right? So this is a sort of switch, right? So each input is getting a time slot, right? So depending upon the value of A, right? So if A is 0, we are connected here. If A is 1, we are connected here, right, for a certain amount of time, right? And then we can have 4 into 1 multiplexer, right? So as I have mentioned, so we have 4 input lines, so we need 2 control inputs, right, A and B, right? So you can see that when both A and B are 0, I0 will be selected, right? And then when we have 0, 1, I1 will be selected, and then 1, 0, I2 will be selected, and 1, 1, I3 will be selected, right? So these are the, and this is the truth table, A, B, right? And F, or you can say Z, right? So 0, 0, I0, 0, 1, I1, 1, 0, I2, 1, 1, I3, right? Okay, and then we have 8 into 1 multiplexers, right? So how many number of control lines we need? So 2 raised to power 3 is equal to 8. So we need 3 control inputs, right? So here you can see that we have 3 control inputs, A, B, C, right? And this is the F, or you can name it Z. So 0, 0, 0, I0 is selected, right? 0, 0, 1, I1 is selected, right? And then so and so forth, and 1, 1, 1, I7 is selected. So, and you can write down the Boolean expression, right? So you can see that we have A bar, B bar, C bar dot I0, right? And then A bar, B bar, C, right? So you can calculate the Boolean expression, right? So this is the generalized equation for 2 raised to power n into 1 multiplexer. So we have 2 raised to power n data lines, n control lines, right? Okay. So this is the logical diagram for the multiplexer. So here you can see this is the block diagram. So we have I0 and I1. So this is S, right? And this is S naught, right? So this is S and this is S naught. So when S is equal to 0, right? So what will be having, we will be having, so let's talk about S is equal to 0, right? So this is 0, so it means I1 is blocked, right? It will not pass through, right? So we will be having a 0. So here whatever the value of I naught is, so let's say I naught is 1, so 1 is passed over here because we have, right? So this will be 1, right? And we will be having a 1. So it means I naught is passed here, right? So when we have S is equal to 1, right? So let's talk about if this is 0, right? So we have 1, 0, same value. So now we are having S is equal to 1, right? So we are having 0, right? And here what we will be having, we will be having a 0 here, right? And then 0. So it means 0 is passed here, right? Right? 0 is passed here. So when we have S is equal to 1, I1 is connected, right? Right? Okay. So this is the circuit diagram for 4:1 multiplexer. So you can see we have two control inputs, right? Rather than calling this truth table, let me call this a function table. So 0, 0, D naught is selected, 0, 1, D1 is selected, 1, 0, D2 is selected, and 1, 1, D3 is selected, right? And then we can have a quadruple 2:1 line multiplexer, right? So here you can see that we have select, right, and enable, right? So we have to select and we have to enable, right? So whenever we have, this is the function table, and you can see that whenever we have enable is equal to 0, right? So irrespective of S, select, all output will be zeros, right? So when enable is 1, right, select is 0, so all A's will be selected, right? And then when enable is 1, S is 1, so we will be selecting B, right? So whenever we have S is equal to zeros, right, 0, A's will be selected, right? And whenever we have S is equal to 1, B's will be selected, right? So we can take the example. For example, we have here 1, 1, 1, right? So here we have 0, 0, 0, 0, right? So enable is 1, right? So here we have 1, 1, 1, 1, right? And select is S is 0, right? So S is 0, so it means we are having 0, 1, 0, right? So we will be having 0, 0, 0, 0, right? And then here what will, right? So here we will be having a 1, right? Select is always 1, right? So here 1, so 1, 0, right? 1, 1, 1, right? So it means I'm having 0, right? 0, 0, 0, 1, 1, 1. So we are having this, right? So it means A's are selected, right? And then when we will be having enable 1 and S is equal to 1, so B's will be selected, right? So that's all for today's lecture, right? So we have discussed about comparators and multiplexers, and we have designed the logic circuit for comparators, right? We started from a single bit comparator, right? And then when we moved to more than one bit comparator, right? So we can compare two binary numbers, right? And we can always know either the two binary numbers are equal, or one is greater than the other, or one is less than the other, right? Then we talk about the multiplexers, right? And we started from the simple one, right? And then we moved to the 4 into 1 multiplexer, and then 8 into 1 multiplexer, and then the quadruple line multiplexer, right? So that's all for today's lecture, and मेरी तरफ से अल्लाह हाफ़िज़, अपना ख्याल रखिएगा, अस्सलाम वालेकुम।